There were many science fiction films made during my childhood in the 90s and early 2000s. A show that I remember from what seems like ancient history at this point was a show called Xenon Girl of the 21st Century. The majority of what I remember from that show seems like a fever dream, but quite a bit of the plot takes place on a space station filled with people living and working in space. Well, we are currently living in the 21st century, and we have had space stations in the past of the likes of Skylab and Mir, and the International Space Station, a space station so large it can be seen as a moving star from the ground, is currently in operation. But these space stations, while marvelous feats of engineering, still pale in comparison to what was effectively a small city in orbit. So what would it take to create humanity's first orbiting city? The very first question most people ask about a project like this is, why? Long before people wonder about the how, the when, or the where, people, especially those in charge of allocating the Earth's scarce resources, will ask, why should time, money, and effort be allocated to such an endeavor? Well, the first answer to this is in the question, Earth's scarce resources. Currently, as a civilization, we have access to the resources of one planet in a vast universe. The idea that resources are limited and about to run out has been the cause for many conflicts throughout human history. Our solar system is filled with raw resources and untapped potential. These resources can be used to improve the lives of people on Earth, as well as reduce the cost of these materials. If these resources are collected in space, they can be refined in space. This gives an opportunity to move a lot of the polluting heavy industries on Earth into space, where their effects on Earth's environment can be greatly reduced. And we can't talk about limited resources without mentioning overpopulation. I'm convinced that the pace of innovation will constantly allow for more and more people to live comfortably on our homeworld if the resources are allocated in an efficient manner. That said, a space station is the first step towards moving away from one planet of resources. After all, an infinite amount of people clearly cannot fit on a planet with finite space and finite resources. An orbital station designed for permanent habitation will have to have adequate amenities for its occupants. The tiny closet-like bedrooms of the ISS will simply not do for a lifetime in space. Living conditions should be more like living in an apartment rather than a permanent camping trip. There's a reason for this size. Humans do not do well in small enclosed spaces for extended periods of time. Having a large amount of people in a relatively small area makes conflict almost inevitable. Another issue is access to nature. If these stations are to be permanent residence to hundreds of thousands of people, access to parks or some sort of nature analog will be required. I suppose virtual reality might be an option, but personally, I find the idea of a bleak environment being artificially alleviated by the use of VR to be quite a dystopian idea, like something out of Black Mirror. This means this station will have to be massive, far too massive to be launched on a single launch vehicle. Similarly to the ISS, the station will have to be constructed in space, either by humans in EVA suits, remotely controlled, or a mixture of both. Components will have to be launched by various launch providers and then assembled in space. The station will have to be designed to be modular to allow for easy construction, repair, and expansion. Some facilities, like factories and labs, do not need to be directly connected to the station. They can be in nearby orbits, allowing inhabitants to travel from revenue-generating centers to living and socializing areas. This allows certain labs and factories to have design autonomy. The residential part of the station will definitely need artificial gravity. Long-term exposure to microgravity can cause issues like bone density loss and muscle mass reduction, in addition to a host of other medical issues. We also aren't sure how possible it is to make healthy children in microgravity. A colony can't really be considered self-sustaining if it can't create more people on its own. To address this, the station will have to be rotating. When a force is applied to an object, it wants to keep moving in that direction. If you tether that object to something, it will rotate around the tether. Think of a ball on a string. When you spin the ball in a direction, the ball rotates around the fixed point. The force that is constantly pulling the ball towards the center is called centripetal force. From the ball's perspective, there is a force pulling it outwards. While this force, called centrifugal force, is not considered a real force, it can be useful for creating artificial gravity. If a cylindrical station were to be rotated, this force will give the occupants the feeling of being pulled towards the walls, and the walls will become the floor. Because of how this all works, the artificial gravity will be weaker near the center. If the radius is too small, the difference between a person's head and feet will be significant enough to disorient them. If the station rotates too quickly, it can cause people to feel nauseous. So the speed of rotation and size of the station has to be carefully considered. So how big will this station have to be? Well, a small urban area can be defined as between 50,000 to 200,000 people. Of course, we can have less people, but if we want our station to be considered a small city in orbit, we need to cater for a population of around this size. Space is at a premium, so living accommodations will be smaller than their terrestrial counterparts. The apartments could be about the size of a large RV at 3 meters wide, 10 meters long, and 3 meters tall. If we make the corridors 2 meters wide and flanked by apartments, we can have a total station width of 8 meters. Each of these apartments should be able to hold 2 to 4 people, similar to the amount an RV of that size would. This means to house everyone, assuming maximum capacity, we would need about 50,000 apartments. It is extremely unlikely that all of these apartments will always be filled to capacity. We would also need space for entering transports, mini parks, and other ways to break up the endless corridor of apartments. Additional space will also be required for education centers, medical facilities, security stations, as well as other offices to assist in the smooth operation of the station. So for our purposes, let's use a circumference of 500 kilometers. If 80% of this is used purely for apartments, one ring will have a total of 80,000 apartments. The standard apartment can be divided for households with less individuals or joined together to create larger units. This ring will have a diameter of 159.155 kilometers and an internal area of 4 million square meters. This is an absolute behemoth of a station, but we aren't done yet. Realistically speaking, we can't just have a station made up entirely of just apartments. If this is a place for people to actually live, we need entertainment, food, and life support systems. Because our station is a ring, we can easily attach another ring for more space while maintaining the current diameter. For the life support system, it's important that the station recycles and reuses as much as possible. This happens largely automatically on Earth, but on the station, all of this has to be done intentionally via life support systems. We need to manage the station's atmosphere, water, sewage, and provide food for the station's occupants. Now that we have living space for residents, we need to keep them alive and comfortable. The first step to that is food. While food can be shipped in from Earth, and some of it most likely will be, the station must be self-sustaining. Because dirt is heavy, we are going to have to go the hydroponic route. On average, a person needs 2,500 calories per day to maintain their weight. This means that the station will have to have an average of 500 million calories available for consumption each day. Calculating the space required for this is going to take a few assumptions. Let's use an example crop to estimate the size of our farm. Of the plants I found that can be easily grown hydroponically, kale seems like the best choice because of its impressive 490 calories per kilogram. To feed the entire station with kale, we would need about 1,020 tons per day. To maximize our limited space, we can grow these plants in tall vertical tubes. If we assume that each kale plant weighs about 200 grams, each ton of kale will have about 5,000 plants. Plants take time to grow, so we need to plant enough food to last until the next harvest. Kale can take between 150 to 220 days to reach maximum yield, so we would need to grow about 153,000 tons, assuming the fastest growing time. This means we will need to be able to harvest 765 million plants every 150 days. There are a few problems with this. We can't just survive on kale, and the station won't only have 200,000 people. There will be tourists and other temporary residents. If we don't only plant kale, we have to take the harvest times and space requirements of these crops into consideration. So taking all of this into account, and the space for technical equipment such as lighting, sensors, and walking space, we can round it up to 10 million square meters for food production. These 10 million square meters can be used more efficiently by using gene modification to increase plant yield and nutrition. Genetic modification can also be used to improve the compatibility of some plants to a hydroponic environment. This will increase the variety of available food choices. Cultured or lab-grown meat can be an additional source of calories and nutrients. Having real animals on the station will likely be an issue. Rearing animals humanely requires a lot of space, which, as we mentioned earlier, is at a premium. Of all of the components of the life support system, atmosphere management is probably the most important. Failure in the other systems might cause long-term issues, whereas a failure in the atmosphere management system will cause an immediate problem, as breathing is very important to most living organisms. Firstly, the system must maintain the habitat at a specific pressure. Earth's pressure at sea level is 101.325 kilopascals, and this is what most humans are used to. We can't fill the entire station with pure oxygen because that would be a serious fire risk, similar to what happened on Apollo 1. The atmosphere on the station can use a mixture similar to the atmosphere of Earth, which is roughly 78% nitrogen, 21% oxygen, and 1% other gases. To generate this atmosphere, we can use water, which is abundant in our solar system. The water can be split into oxygen and hydrogen using electrolysis. The oxygen can be used to provide breathable atmosphere to the station, and the hydrogen can be used as rocket fuel. On average, a human uses about 550 liters of oxygen per day. This means to sustain a population of 200,000, we would need to produce 110 million liters of oxygen. A space station like this is almost guaranteed to have a large tourist presence, so significant overhead would be advised. So to be on the safe side, let's budget for 100,000 extra people. This means that 165 million liters of oxygen has to be made available per day via electrolysis. We do have another way to produce oxygen: photosynthesis. Put simply, photosynthesis is a process that breaks down carbon dioxide and water into oxygen and carbohydrates. An estimated 500 milliliters of oxygen is produced per square meter of leaf surface every hour. If we assume our hydroponics area is covered in leaves, we can produce about 120 million liters per day. This is assuming that these plants do well under 24-hour artificial lighting, because not all plants do. This is also not the 165 million liters that we need, but it will offset the amount required and provide some additional redundancy. Plants can also absorb carbon dioxide. If we assume each square meter of plants absorb 1.68 liters of CO2 per hour, our food system, which is 10 million square meters, will be able to process about 403,200,000 liters of CO2 every day. To put that into perspective, a human exhales about 500 milliliters of CO2 every day. Water, like most things on the station, will have to be recycled. And when I say water, I mean all water. Ideally, even sewage will be processed to the point that it can be reused. Currently, there are proposed treatment ideas that convert raw sewage back into water and even produce edible bacteria. Firstly, the grey water will have to be separated from the black water. Black water is wastewater that has come in contact with human waste, while grey water has not. Solid human waste has a higher chance to contain dangerous pathogens, so grey water is easier to recycle where it was generated. The black water will be sent immediately to the central waste processing, where all of the liquid will be removed and purified for reuse. The remaining solid waste will be broken down by bacteria. This will produce methane, which can be collected and stored as fuel. The remaining mass can be broken down further to generate carbon dioxide that can be used to generate additional methane or cultivate algae. Phosphorus, potassium, and sulfur can be extracted from urine. These chemicals can be useful in food production. The waste processing also produces some amount of nitrogen, which can also assist in food production and provide nitrogen to pressurize the station. So this station will have one residence ring, 3 rings for life support and food production, and 1 commercial ring. None of this will be possible without an adequate supply of electricity. As the station is in space, with almost constant access to the sun, solar energy is likely to be the best source of power. The edge of the rings can be covered with solar panels to harness this resource. The station will also need to manage heat. The side of the cylinder that faces inwards is almost always shielded from the sun. Radiators can be placed here to radiate away the station's excess heat. To justify building a station of this magnitude, there has to be some potential for return on investment. A station like this has a variety of ways to generate revenue. The first, and perhaps most obvious way, is tourism. Our planet might not always look beautiful on the ground, but from space it is absolutely breathtaking. Giving people an opportunity to view our planet or the stars in comfort can be a source of revenue. Another advantage of being in orbit is the lack of gravity. While the station itself can have gravity, the center of the ring can remain stationary to allow for a microgravity environment. This can be used for both scientific and tourism purposes. With current technology, a seat to space can cost $52 million. and a night stay on the ISS can cost up to $35,000. This is nowhere near sustainable. In order for tourism to work on a station like this, the cost to get to and stay on the station needs to be significantly less. While there might be people right now who can afford this, there are significantly more people who can't. Lowering the price to a reasonable level allows for a wider customer base. Fortunately, larger spacecraft with the goal of reducing these costs are in development. As I said earlier, the station can take advantage of a stationary center which will allow for a microgravity environment without requiring the workers to live in that environment. In addition to this, larger production facilities can be built off-station or within traveling distance. One possible industry that can benefit from microgravity is the manufacturing of human organs. Yes, you heard that right. Scientists on the ISS are currently testing methods to 3D print human organs. The process requires microgravity, which this proposed station will have access to. Having organs on demand can make reliance on donors a thing of the past. Another option is spacecraft manufacturing. Every satellite or spacecraft in space right now, except the ISS, was launched whole from the Earth. This means it was constructed to handle an environment that it would not experience again after launch. Anything launched from the Earth needs to be able to withstand the relatively rough launch conditions and fit into the fairings of launch vehicles. Launch providers tried to make smoother rides and larger fairings, but what if no ride or fairing was needed? If the spacecraft were to be constructed in space, it would not need specialized hardware to survive the vibrations and g-forces of launch. Limitations in fairing sizes would also not be a factor. Components can also be made more substantial as they would not need to be folded or unfolded. This can open up the possibility for truly massive satellites and spacecraft that are impossible to launch from Earth. If you live on this station, your apartment will be about the size of a large RV. It is unlikely that separate bedrooms will be possible in the standard unit size, however multiple beds may be able to fit into one room. For example, you can have one large bed and a bunk bed fairly well separated. You can prepare your meals in your kitchenette and enjoy them in a small dining area, and then relax in your living room, which is right across from your dining area. You will have access to a washing area as well as a small study. In your kitchenette, bedroom and living room, you will have access to windows to the outside. They're very small, but enough to see out of, about 50 centimeters in diameter. The residential and the commercial rings will be the rings on the edges and therefore the only rings with wall-mounted outside views. Some of the housing will be in the commercial ring and some commerce will be in the residential ring. So depending on which ring you live on, you'll either have a view of the Earth or a view of the stars. Real estate on the inside area will have views looking inwards towards the ring system. While obstructed, this view will still be magnificent. The station will rotate 4.5 times every hour since it is rotating about 2,249 km per hour. So looking out of the window, your view of the stars or Earth will be constantly changing. You leave your apartment through a door in your kitchen. This leads you into the main hallway with your neighbor's doors being right across from yours. The station hallways are 2 meters wide, so enough for 2 people to walk comfortably side by side. The walk around one ring is about 500 kilometers. It's walkable, but that's about 12 marathons. Fortunately, there will be access to a public transportation system every 1 kilometer around the station. These transit stations can also be used for getting between the different rings. If you work in agriculture or in the commercial sector, your job is just a short walk and a train ride away. If you work in the microgravity facilities, you'll have to take an elevator towards the center of the ring. As the elevator rises, you'll feel yourself getting lighter and lighter as the effects of the spin gravity reduces. Once you arrive at the center, you'll be able to do your job in microgravity for 8 to 9 hours before returning to gravity at the end of your shift. If your means of employment is off-station, you'll have to take a shuttle from the docks to your place of work. From the tourist side, things are a little different. Your experience starts when you book your trip to the station for a modest price. You will likely be taken to the station on a Starship-type vehicle. Capsule-type vehicles at this time have a very small carrying capacity, which means the per-seat price will be very high. After spending some hours in space, you will see the station slowly come into view as the spacecraft begins its final approach. Once docked, you will proceed through the airlock. As the elevator begins to descend, you feel your luggage, and yourself, slowly increase in weight as you get closer to the edge of the ring. When you arrive at your ring, a transport takes you to your hotel. Your hotel is similar to the apartment except smaller, about half the size of a full apartment at your current budget. You'll have your own washroom, your own bed, and a desk to eat and work at. From your window, you'll be able to see the Earth or stars depending on your location. You'll have access to attractions unique to the space station, such as stargazing or microgravity concerts. At the end of your trip, you'll collect your belongings and memorabilia and make your way towards the elevator. As you ascend, you feel yourself and your luggage slowly become lighter. You'll enter the spacecraft. After a short wait, the hatch closes. You hear the familiar sound of the spacecraft's RCS as it pushes itself away from the station. Eventually, the spacecraft fires its main engines to begin its deorbit burn, and you are officially on your way back home. A station like this is unfortunately still in the realm of science fiction for the next few years, if not decades. The methods they use at that time will likely surpass anything I can imagine or research. Perhaps they will find ways to make it even larger or more comfortable, or maybe they will skip it entirely and go straight to an O'Neill cylinder. Either way, what seems to be true is that humanity's future is among the stars.